Good afternoon, everyone, and welcome to the second seminar of Alexandros Karam for the Institute of Physics in Opava. Today, he will talk to us about scale invariance in particle physics and cosmology. Alexandra, you may begin.
Hi, everybody. Thanks again for the invitation. Today's talk will be rather different to yesterday's. There is no Palatine gravity today. So I will talk to you about scale invariance in particle physics and cosmology. Now, as you all know, it's been 10 years already. Back in 2012, the Higgs boson was discovered, which was the last missing piece in the standard model of particle physics model, the standard model of particle physics. And after it was discovered, the model was complete. It was the last particle that was left to be discovered. So we have a standard model, which is very good. It can describe the three of the four interactions, the strong nuclear, the weak nuclear, and the electromagnetic. These are the gauge bosons. These are the 6 quarks, and these are the leptons. But nevertheless, the standard model has a few problems, or rather, there are some phenomena that it cannot explain. These are dark matter. There are no particles in the standard model that can explain the measurements of extra non-baryonic mass at galactic and cosmic scales. The standard model does not explain how neutrinos obtain their mass, because these neutrinos have very small masses, but they do have masses. However, the standard model predicts them to be massless. Also, as we will see later, because of the measured value of the Higgs mass, which is around 125 GeV, the Higgs quartic coupling, which runs with energy, becomes negative at high scales, which means that the Higgs potential becomes unstable. Furthermore, standard model does not explain why there is more matter than antimatter in the universe. Also, why there are 6 flavors of quarks and leptons with different characteristics. Also, why QCD does not break the CP symmetry. And why the 3 gauge forces of the standard model seem to become unified at a high energy scale. Finally, this is not exactly true, but we still don't know the particle physics description of inflation, but there is the possibility that the Higgs boson could play the role of the inflaton if it's non-minimally coupled to gravity. And more. Now, this is let's see how the Higgs field enters the Lagrangian of the standard model. This is the potential, the Higgs potential, which contains 2 terms. This is the mass term, and this is the quartic term. Then the vacuum expectation value and the mass of the physical Higgs field are generated through this scale mu Sm. So the VEV of Higgs is 246 GeV, and the mass is 125 GeV. Now, this coupling, lambda h, the quartic coupling, is not actually constant, but it evolves with energy. And how it evolves is described by the renormalization group equation, or RGE, which has this form. And as you can see, it contains the couplings of the rest of the particles and forces of the standard model. So we have G1 and G2 for the U1 and SU2 gauge symmetries. And we also have the Opava of the top quark. Now, what's interesting is that because of the high mass of the top quark, its Opava coupling is large. And since it enters with a negative sign here, it forces lambda to become negative at high energies. So this is the running of the quartic coupling at 3 loops. And as you can see, around 10 to the 11 GeV, it becomes negative for the measured values of the Higgs mass and the top quark, which are these. Now, this would not have happened. This would not happen if the mass of the Higgs was above 129 GeV, or the top quark mass was below 171. But the fact that it happens is bad, because it means that there is now a new minimum, which has a much lower energy. And there is always a chance that this is our electroweak vacuum, electroweak minimum here. So there's always the possibility that we will tunnel to this other minimum, and the universe will be destroyed. However, because these values for the Higgs mass and the top quark are very close to these values for which we would have absolute stability, we have determined that we live in a metastable universe, because the probability of vacuum decay is really small throughout the age of the universe. So from the Big Bang to today, the probability that the vacuum decay has happened is really small. It's around 10 to the minus 1000. And we also do not expect it to happen for many years in the future, for the lambda CDM model, for 10 to the 800 years in the future. So it's a problem, but it's not that bad, since we see that the lifetime of the universe is great. However, from a theoretical point of view, we would like not to have this problem. We would like our vacuum to be absolutely stable. In order to achieve this, we should add scalar fields that couple to the Higgs in order to achieve vacuum stability. This is because scalar fields come with a positive sign and the RG of lambda, and this means that they would lift it up. So this is the first conclusion. Now, various solutions to the problems I mentioned in the beginning typically require the introduction of new particles at high scales. Now, along with these particles comes a new, typically new large scale of new physics. And these new particles at these high energies give loop corrections to the Higgs boson mass of this form. So in order to get the measured Higgs mass, which is 125 GeV, the bare Higgs mass has to be extremely fine-tuned with the correction, which is quite unnatural to do. It requires a huge amount of fine-tuning. Now, the most popular solution to this problem is supersymmetry, if supersymmetry is broken close to the electroweak scale. But an alternative solution is classical scale invariance. So since there has been no supersymmetric particle found by the LHC, it would be nice to explore some alternatives. So a theory is said to have a classical scale symmetry if the Lagrangian is invariant under these transformations. And what's interesting is that there is only one scale in the standard model, which is this parameter mu SM we talked about earlier. Now, without this parameter, the standard model is classically scale invariant. The quadratic sensitivity to the cutoff is now non-physical. However, quantum effects break the symmetry through the running of the couplings, but this does not reintroduce the quadratic divergences. This is the famous Bardeen's argument on naturalness. Therefore, we have a solution to the hierarchy problem. Now, imagine then that we have a scale invariant theory without any mass scales. How will we break the symmetry and generate masses for the particles? This was answered by Coleman and Weinberg back in 1973. They studied a very simple model of massless scalar quantum electrodynamics, which is given by this Lagrangian. They computed the one loop effective potential, and they saw that at one loop, a minimum is generated. Therefore, the symmetry is broken at loop level, and we can have a mass for the scalar, which is related to the mass of the vector boson of this new U1 symmetry. This is also called dimensional transmutation, this effect of generating a mass scale from one-loop correction. Now, if we were to apply this mechanism to the standard model, because of the very large mass of the top quark, we would find a negative mass for the Higgs. So if we were to start with a scale invariant potential, so without this term for the Higgs, unfortunately, we would find a negative physical mass for the Higgs boson. So in order to get a positive mass, we should add bosonic fields in our theory. So imagine we construct a scale invariant extension of the standard model, then we would need bosonic fields in order to obtain a positive mass. Because the bosonic fields enter with a positive sign. Now, there are many scale invariant models that have been proposed in the last few years. Most of them are weakly coupled, but some of them are also strongly coupled. I will focus on weakly coupled models. Now, personally, I studied classical scale invariant extensions of the standard model for my first two papers back in 2015 and 2016. The first one contained a model which was standard model cross SU2 plus a real singlet and three right-handed neutrinos. And the second one was standard model cross SU3, which had interesting and rich dark matter phenomenology. Now, recently, after all these years, with Maciej Kierkla and Bogumiła Zwiziuska from Warsaw, we studied again a scale invariant extension of the standard model with an enlarged with an SU2 gauge group. Because there have been some recent developments, and we wanted to do some computations more rigorously and see how some conclusions that other papers claim to have may be true or not. So we studied the classical scale invariant standard model cross SU2 gauge group. The new fields are one complex scalar doublet phi under the SU2 and three gauge bosons X. In the unitary gauge, we can write our fields like this. And the one loop effective potential in terms of H and var phi has this form, where this is the tree-level part. This is the quartic coupling of the Higgs. This is the quartic coupling of the second scalar. And this is what is called the portal coupling between the two scalars. While this is the one loop potential, which is given by the Coleman-Weinberg formula, which contains the masses, all the masses of the model. And these are some constants here. Now, from the tree-level potential, we can compute the tree-level field-dependent mass matrix, which has this form. And from this mass matrix, we can find the mass eigenvalues, which are given by this formula. Now, there are also the Goldstone bosons, which have these masses. And at tree level, we have the W plus minus mass, the Z boson mass, the top quark mass, and we also have now the mass of the extra gauge of the 3 extra gauge bosons, which is 1/2. Gx is the new gauge coupling, and this is the second scalar field. Now, if we minimize the one loop potential, we have these expressions. Typically, the new VEV, the VEV of the new field is much larger than the electroweak VEV. Therefore, this term, which is here, can be neglected. Then the second minimization condition takes this simple form. While the first one, if it's expanded, it takes this form. So the above shows that the symmetry breaking in the var-phi direction is of Coleman-Weinberg nature, while along the Higgs, the H direction's character is standard model-like, with the 3-level mass term being generated by the portal coupling. Now, the physical mass corresponds to a pole of the propagator, i.e. it's evaluated away from momentum 0, and is given by this formula. So including the loop corrections from the self-energies, we obtain a momentum dependence, which is given here. So what we need to do is compute this one loop self-energy Feynman diagrams in order to find these corrections here. So after we do that, the new eigenvalues are given by this. So you can see we have the corrections with the self-energies. And in order to obtain the momentum corrected masses, we have to solve the so-called gap equations, which are computed at when the momentum, which are computed on shell when the momentum is equal either mh or ms. So the physical eigenvalues, mass eigenvalues, we name with capital H and capital S. So the first one we identify with the physical Higgs mass of 125 GeV, and it can actually be used to fix the quartic coupling lambda H. Now the mass eigenstates can be obtained from the gauge eigenstates by a rotation matrix of this form, excuse me, where the rotation angle theta has to be in this range. Now, in our numerical procedure, we followed these steps. So the main point is that we chose as our input parameters mx and gx, so the mass of the extra gauge bosons and the gauge coupling. We assume the 3-level relation to be this, so we can compute the value of var-phi VEV, the var-phi VEV, V var-phi. And the values of gx and the VEV of var-phi are treated as evaluated at the scale mu equals mx. Then we use the minimization condition along the var-phi direction, evaluated at mu equals mx to evaluate lambda var-phi. So we use this condition evaluated at the energy scale equal to mx. So if this is mx, then this is 1. So all of this is 0. And then it's just this multiplied by -1/3. So we get this simple relation. Then we evolve gx and lambda var-phi from mx back to mz. Remember that mx is typically much heavier than mz. Also, we impose this condition on at mz, namely that the value of gx is smaller than 1.15, so that the RG improved potential is well behaved throughout the scales we consider. Otherwise, we will have lambda opoles, and it will be bad. Then the portal coupling as a function of lambda is found from the first minimization condition, which was this one. So we obtain the portal coupling from this. And then, as I told you before, the value of the Higgs-Corti coupling is computed from the requirement that the physical Higgs mass is equal to 125 GeV, i.e. from this gap equation. So the evaluation is performed at MZ. Therefore, we need the expectation value of var phi at MZ. Remember that also the vacuum expectation values run with energy. And it can be found from the second minimization condition. Then we solve the second gap equation to obtain the mass of S iteratively. And finally, the mixing between the scalars is evaluated by demanding that the off-diagonal terms of the mass matrix evaluated at zero momentum and in the mass eigenbases are zero. So this is our algorithm. And by doing so, we only have two input parameters, mx and gx. And everything else is automatically calculated. Now, these are the renormalization group equations of the couplings of the model. This is the RG of G1, G2, G3 of the new gauge coupling, GX. This is the RG of the top Opava coupling. And these are the scalar couplings. As you can see, the RG of lambda receives a positive contribution from the portal coupling, and this can help it get stabilized. Now, in the gauge sector, we discussed already that this is the mass of the 3 extra gauge bosons. But what is also interesting is that the system possesses a Z2 cross Z2 prime symmetry, which corresponds to a gauge transformation and a charge conjugation of the group elements. Therefore, these three gauge particles are stable, and they can be dark matter candidates since they are stable. So these extra gauge bosons can annihilate through the scalars H and S to Z bosons, W's, or standard model fermions. They can also annihilate to H and S through these Feynman diagrams. But what is also interesting about this model is that due to the non-abelian nature of it, we can also have what is called semi-annihilation, where two gauge bosons interact and produce one gauge boson and one scalar. And it turns out that these diagrams are quite important. So regarding dark matter, this is the Boltzmann equation, which describes the evolution of the number density of the dark matter particles. It turns out that for the annihilation processes, all of these, the dominant one is the one where two x's go to S and S, this one. And a simple approximation is to write the thermally averaged cross-section times the relative velocity in this way, even though the full formula is, of course, much bigger. And we also have to include all the other processes. Furthermore, the semi-annihilation cross-section is dominated by the XX to XS process. So two gauge bosons going to one gauge boson and one scalar, the second scalar. And the thermally averaged semi-annihilation cross-section times the relative velocity is given by this formula. And you can see that the latter is actually around 5 times larger than the former, which means that the semi-annihilation processes are actually more important than the annihilation ones. Then, if you solve this differential equation, you can obtain the dark matter relic abundance. And what we see is that in order to reproduce the measured value of the dark matter relic abundance, this relation has to be satisfied between Gx and Mx. Now, these dark cage bosons can also scatter off nucleons with this diagram, and the spin-independent cross-section is given by this formula. And based on the latest constraints, we will need to have Mx above around 900 GeV. We will come back to this later. Now, this model that I just described was first proposed back in 2008 by Thomas Hamby, although back then Hamby considered the non-scale invariant version. But he didn't compute the dark matter abundance, or he didn't take into account the semi-annihilations, for example. Then in 2013, himself, along with Strumia, considered the scale invariant version of this model. Although, again, they made a lot of simplified assumptions. Around a month later, Christopher Caron and Raimundo Ramos studied the same model, but also themselves, they didn't take into account the semi-annihilation processes. Then a student of Strumia's again considered this model, and he actually did things properly and rigorously. And about the same year, Valiakos, Christopher McCabe, and Gunnar, along with some other models, focused on the vacuum stability of the model. And they found that in the lambda portal versus Gx, this is Gx plane, this black region, the region contained in this triangle, actually stabilizes the Higgs potential. So if Gx is approximately above 1 to 1.8, 1.9, and the portal coupling is above 10 to the minus 2, the Higgs potential can be stabilized. And in this range, the second scalar mass is around 100 to 200 GeV. Now, around 2015, as you know, gravitational waves from the merger of black holes were discovered, which opened up a whole new field of physics. And many people started working on gravitational wave physics. One avenue to generate gravitational waves is through a first order phase transition when symmetry gets broken, for example. And since it turns out that scale invariant models can, because of the form of the potential, they can provide a very strong first order phase transition, which guarantees the generation of gravitational waves. So it's nice to consider these models because we can have the dynamical generation of scales, we can have successful dark matter and gravitational waves, which may be explored in the near future. So there was something missing here. Anyway, so yeah. So in order to study phase transitions, we need to compute the finite temperature potential. So we need to, which is given by this formula, which is a bit complicated because it contains contributions from something called daisy diagrams. And this is what the potential looks in terms of the temperature. So we start with a potential which is symmetric around the origin, and as the temperature drops, a new minimum arises, and we have a critical temperature. Then as the temperature drops, this minimum becomes shallower and lower than the minimum of the origin. And eventually it settles at zero temperature. So let's examine what happens during the evolution. So as I told you, there's the critical temperature where the two minima degenerate. And at this temperature, we can also have tunneling. Then as the temperature drops, we can have a vacuum domination era. Therefore, we can have a few e-folds of thermal inflation. And this causes what is called supercooling, i.e., if the phase transition is delayed to low temperature, much below the critical temperature, it is possible that the period of thermal inflation due to the false vacuum energy appears before the phase transition completes. So because there is latent heat in the system, we can have a period of thermal inflation. Now, the onset of the period of thermal inflation can be approximately attributed to the temperature at which vacuum and radiation contribute to the energy density equally. So we can obtain a value for the temperature, for the thermal inflation temperature. Then, this is a plot which shows the critical temperature and the vacuum domination, the inflation temperatures. And as you can see, they're of the order of TV. This is log 10 of temperature. Now, as you can see, there are a few regions that are excluded here. This region with low MX, this is also log scale. So the values start here from around 350 GeV. Now this region is excluded because it is not possible to reproduce a stable minimum with the correct Higgs value and mass in this regime. Now the upper right corner is cut off by the condition on GX I mentioned before. It has to be smaller than 1.15 at the MZ scale. Here, this region is excluded because lambda runs to lambda poles, the Higgs lambda. And this region is excluded by the percolation criterion that I will describe later. And also in this region, the phase transition is sourced by the QCD phase transition, which is complicated to analyze. So we assume that that this is not the case. Anyway, after that, we have what is called the nucleation temperature. which is defined as the temperature at which at least one bubble is nucleated per Hubble volume. And this is actually interpreted as the onset of the phase transition. Normally, in order to obtain the nucleation temperature, one has to solve the bounce equation with these boundary conditions, and then compute the Euclidean action, and from that obtain the decay rate of the false vacuum. And the most common criterion for evaluating the nucleation temperature is this one. But recently it has been shown that it is not reliable in the case of strongly supercooled transitions, as it is the case in our model. Then after the nucleation temperature, we have the percolation temperature, which is basically when the phase transition is said to be complete. And is when the gravitational wave signal is generated. So the probability of finding a point in the false vacuum at a certain temperature is given by this, where this I is the amount of the true vacuum volume per unit moving volume, and is given by this complicated integral. This Hubble parameter here can be split in this way, depending on if the temperature is above or below the thermal inflation temperature. And using that, we can compute eventually the integral and find that the percolation criterion is this one, which basically says that the fraction is the ratio of the volume in equal size and randomly distributed spheres to the total volume of space for which percolation occurs in a three-dimensional Euclidean space, and implies that at this percolation temperature, at least 34% of the volume is converted to the true minimum. So this is when the phase transition is said to be complete. Actually, the percolation and nucleation temperatures are of the same order, of similar order. But if you compare these temperatures with the critical and the inflation temperatures, these are actually 3 orders of magnitude less. So these are of the GeV order, and these were of the TeV order, which means that we have strong supercooling. Also, one needs to make sure that the volume of the false vacuum is decreasing around the percolation temperature. This condition is especially constraining in models featuring strong supercooling, as the thermal inflation can prevent bubbles from percolating, and it's expressed like this. So because of that, we find this region here, which is excluded. So in the end, this is the allowed parameter space that we have. So Mx needs to be between 300 GeV to 10 to the 3 times 10 to the 5, also this region, and Gx can be from 0.7 something up to 1.07. So furthermore, after the phase transition completes, we have the so-called reheating temperature. So this is when the total energy, when the whole energy is turned into the energy of radiation. Now, on the other hand, if at the percolation temperature, the rate of energy transferred from the var5 field to the plasma is smaller than the Hubble parameter, then the energy will be stored in the scalar field oscillating about the true vacuum, and it will redshift as matter until this decay rate becomes comparable to the Hubble parameter. So in this case, the reheating temperature will be given by this formula. So we have two cases. And it all depends on if this decay rate is smaller or bigger or larger than the Hubble parameter at the percolation temperature. Now, the rate of the energy transfer from var5 to the plasma is given by this formula, where gamma SM denotes a decay width computed as in the standard model, i.e. with the same couplings and decay channels, but for a particle of mass ms, so not for the Higgs, for the other scalar. And we also have this term, which contains the decay rate of the S scalar to Higgses. And it's quite important. Now, what we find in our model using the above analysis is that gamma phi is actually a lot bigger than H in all of the parameter space. You see that the ratio is bigger than 1 for all of the allowed parameter space. This will prove to be really important. So now, because of this supercooling effect, we start with a hot universe with massless particles, but due to the thermal inflation, we end up with a cool universe where the massless particles are diluted. And then after the phase transition and reheating, we have a reheated universe with diluted massive particles. So in 2018, Hamby and Strumia, along with Teresi, proposed the supercool dark matter scenario. So normally, dark matter is produced via the freeze-out mechanism, as I explained before. But they explained they proposed a new mechanism for producing dark matter. So they studied this SU2 model, and we'll see now what they did. Similarly, Baltes and Garcia Selly studied the same model, and then also Marfatia and Cheng studied again the same model in 2020. And both of these papers closely followed the analysis of this paper. But we'll see that we actually disagree with them. So their assumptions were that assuming that the true vacuum has zero energy, the energy in the false vacuum is given by this. This should be mx capital, which implies that supercooling starts at approximately mx over 8.5. This is actually not a bad approximation, but all of them again assume that nucleation occurs when this ratio is about 140, but as I told you before, this is not true for strong supercooling. They also assume this relation between the reheating temperature and the thermal inflation temperature. This is true. But the problem is that they assume this very simplified expression for the decay rate. But as we saw, this has to be like this. And what this does is that, as I showed in this plot, it makes the decay rate to be larger than the Hubble rate. Therefore, from this formula, we always have the reheating temperature to be equal to the thermal inflation temperature. Therefore, we have instantaneous reheating. Now, assuming we have these dark matter particles, which are originally massless, the inflationary supercooling dilutes them in this way. And then we have two cases. For the reheating temperature smaller than the decoupling or freeze-out temperature, which is normally computed to be around mx/25, we have a supercooling and subthermal production, which contribute to the dark matter relic abundance. So the total relic abundance is given by the supercool abundance plus the subthermal population, which arises from scattering with the thermal bath. While for reheating temperature above the decoupling temperature, the plasma thermalizes again, and the usual freeze-out mechanism yields the relic abundance. So in this paper, they distinguish these two cases, and they find this parameter space for their model. So this line corresponds to the usual freeze-out mechanism. However, see that here that they assume Gx to go up to 10, which we cannot have since we have imposed the constraint that at mz Gx has to be smaller than 1.15, otherwise Landau poles arise. And this is the supercool plus subthermal production. But and this is a similar plot from this other paper. But what we find is that due to the percolation criterion, which excludes mx above 10 to the 6 GeV, and the fact that we have in the rest of the dark matter range, there's this condition, we find that the reheating temperature is always larger than the decoupling temperature. And because of that, we only have the standard freeze-out mechanism. Therefore, in these plots, we claim that this is not true. We cannot produce, this model cannot reproduce dark matter via the supercooling mechanism. And we only have the standard freeze-out mechanism, which is in this small region. So what we find is that indeed we can only reproduce the measured dark matter abundance if mx is around 1.1 to 1.5 TeV. And furthermore, because of the recent constraints from the LC experiment, the direct detection spin independent cross section tells us that only this parameter space is allowed now, which corresponds to Gx around 0.92. So instead of all this big parameter space, we find this tiny parameter space to be allowed. So now, I don't have much time, I assume. So what, during the phase
5 minutes.
Okay, during the phase transition, there is a lot of energy in the bubble. The bubble contains the true vacuum, and it expands in a sea of false vacuum. And then as more bubbles are created, they collide, and they produce sound waves in the plasma. There is also turbulence in the plasma, and yes, hydromagnetic turbulence. So we have, in general, we have 3 mechanisms to generate gravitational waves. It's from bubble wall collisions, it's from sound waves, and from turbulence. However, the computations for the gravitational wave spectrum arising from turbulence are not to be trusted, because they're not quite robust yet. So we will only focus on bubble wall collisions and sound waves. So without going into detail, these are the spectra from bubble collisions and sound waves. And for the allowed parameter space that I showed you before, we find these gravitational wave spectra. And they fall within the observability window of the LIS experiment. So in the future, this experiment will become operational. And if it sees gravitational waves, then our model could be falsified. So if I assume that you know that LISA is a laser interferometer space antenna, it will be these three devices will be sent in space. They will have a separation of 3 million kilometers, and they will be able to observe gravitational waves, hopefully. So I guess I have no time. So I will finish, but I will just mention that in a similar way, we can generate the Planck scale, and we did this in this model with in this paper with Thomas and Professor Tambakis. But let me just skip to the conclusions and say that scale invariant models are minimal extensions of the standard model that can solve many of its problems. In them, all mass scales are dynamically generated. What's nice about them is that a strong phase transition is guaranteed due to the shape of the potential. This can lead to supercooling and potentially observable gravitational waves. Thank you.